Hello, welcome back. In this lecture, we are going to start to discuss binary trees. So this is chapter 16 about binary trees. So the major topics we are going to cover include the definition of binary tree and then binary search tree. This chapter majorly discuss about binary search tree. Okay, then we are going to discuss some operations in binary search tree, including like search, insert, and delete in a binary tree, and also discuss the traversing. Okay, so the traversing, there are two kinds of traversing. We are going to go over depth first traversal via recursion, okay, and the breadth first traversal. It's a level order, so we are going to see how are we going to do the traversing. And then we are going to discuss how we use Java language's tree set for the binary tree operation. And lastly, it's going to be about the application of binary tree concept about Hoffman coding. Okay, so in the first section, it's about the definition of binary tree. So binary tree anyway, it's also a tree structure. So let's first take a look at the features for tree structure. So a tree structure is composed of a number of nodes, and the nodes are connected by the directed edges or arcs, we call it. And be careful, the keyword directed. Okay, so there is a direction for the edge. And because the edge has direction, and specifically here for tree structure, okay, it's a open one, okay, not a closed one, closed one structure, okay. So it's a cyclic structure. So there is no circle. And also, there is a feature is there is only unique path between any two nodes. Okay, and also tree structure is a hierarchical model. Okay, so hierarchical model, that means there's some hierarchical relationship between the nodes. Okay, so there's parent node and child node concept. And also at the very top, the node at the very top of the hierarchy, we call it a root node. So keep this in mind, root node. That's a very important concept in tree structure. And also there is only one root node. Okay, so be careful, only one root node. And it does not have any incoming edges. So root node does not have incoming edges. And all other nodes have exactly one incoming edge. Okay, and this is because the relationship between any two nodes, the connection is directed are edges. Okay, and because of directed edges, and but of course over here we also define it can only have one income, not multiple incoming edges. So these are the general features about tree structure, okay, here for the definition. And then let's take a look at binary tree, okay. So a tree can have multiple branches. So if the tree, each a node can only have two branch, then we call it a binary tree. So two branch means each node has at most two child nodes, okay. So in tree structure, we have the definition node. So here each circle is a node. So we have node. Okay, so each circle here is a node. And the connection between the two nodes and also with the direction here, we call it an edge or arc. Okay, so this is a directed arc, edges. And also because tree structure is a hierarchy. Okay, so here it has a parent and a child relationship. Okay, so for the edge, the direct edge is point to, so that is going to be child. And the point from, the coming from, then that's defined as parent node. Okay, and also we know at the very top of the hierarchy is the root node. And also when we discuss binary tree, we also talk a lot about subtree. Okay, so subtree basically it's its branches. Okay, so like in this case, node G, the root node. Okay, it's a left branch. This big circle. This is node G's left subtree. So node G's left subtree. And this big one is right branch. Okay, then it's right subtree. Okay, so similar like here for node F, then this part, okay, then this is node F's left subtree, okay, and similar like over here, is it so? Then this is J's right subtree. Anyway, so from the branch, then of the following going to be its subtree. Okay, so subtree concept also. Okay. It's not just a single node. Okay, single node then is called a child node. Okay, left child or right child node, and also keep that in my hierarchy. Also have parent node. Okay, so that's the feature for binary tree. So then, how do we implement a binary tree structure? So binary tree, ADT, okay. So it can be implemented using linked structure. If you recall previously in linked list, that's a linked structure. So linked structure, it has a node, is it? And the node also has a pointer, point to the next node. So because of this, all of the nodes chained together, But linked list, it's a linear data structure. Okay, and here our structure is a tree structure. So how do we link the node? Is it together? Okay. So in tree structure, the node then, and here, because it's a binary tree, it only has two branches. Is it? So here, this is a basic building unit. We call it a bin node. Okay. And so similar, it has but it has three parts this time. It has the data parts, so similar as the node in linked list, but it has two pointer. Okay, one pointer to left, the other pointer to right. Okay, so when we implement binary tree using linked structure, then the basic building unit is bin node. The bin node has three parts, okay? The data part and the two reference pointer, two pointer point to other bin node. Okay, so another bin node. The basic right is also another bin node. Okay, so it point to some other bin node for its left, then to connect its left subtree and right subtree. Okay, so that's how we implement a binary tree using linked data structure. Okay, so here we also gave the bin node UML diagram. Okay, so it has the data on the left and the right. As previously explained, left and the right, the type are bin node. Okay, and we can provide two constructors. Okay, so that's the basic features and the data structures for binary search binary tree. Okay, the basic building unit is the bin node. Bin node has two pointer. Okay, one is left and one is right. Okay, and then there's a so this whole chapter basically is about a binary search tree. Okay, so previously discussed binary tree. So then what is binary search tree concept? Okay, so binary search tree, the concept is it is a specialized type of binary tree. Okay, and it has special requirement. It's all elements in the left subtree must be less than or equal to the root node. And all elements in the right subtree must be greater than the root node. So you must maintain this kind of ordering, okay? So whenever we try to insert a new item into the binary search tree, this ordering rule must be strictly followed. So any values in the left subtree of a node, then going to be less or equal to the node values. And all the values, so the values come from the right subtree nodes, they must be greater than the value in the node. So this is the ordering rule for binary search tree. Okay, so keep this in mind. And also in a binary search tree, item must be unique, so no duplicates are allowed. Okay, so then what's the benefit for binary search tree? Is it compare like with linked list? Is it okay? So why we build a so complicated tree? Okay, so the benefit for it, once you build a binary search tree, then the lookup, so the search of one item is going to be faster. Okay, and because this follows similar concept, if you remember the binary search. Binary search is each time when you do say cut by half, is it? So the big O is log 2n. Okay. So similar for binary search tree, is it? Because of this special ordering true rule, this special ordering rule. So for binary search tree, okay, the search is also going to be log 2n. Okay, so it's faster, but not like a binary search. Binary search, all items must be ordered already. Okay, so here there is no such a requirement. No such order requirement. Okay, so that's binary search tree, okay, the benefits. Okay, and then because of the special features for binary search tree, okay, suppose we have this sequence of number and we want to build a binary search tree, is it? So how do we build that with that requirement, is it? So we start with 55, okay? So then this is going to be the root node. And then 50. 50 then should go to the left, is it? Okay, so it should be its left child. Then 38, okay? So the way to build the tree, we start there at the root node. You compare it's less than 55, so it should go to its left, okay? And then you come compare with this node, it's less than, so then you insert 38 and then 51. Okay, so 51 is less than, so we should go to left. And then 51 is greater than 50, so it should go to its right. The right doesn't have any node, so you just directly add a new node. Then 39, same thing. So 39 is less than, we go to left, and then move to this child node. You compare 39 with 50, it's less than, so you go to the right. Then 39 compare with 38, it's greater, so it should go to the right. There is no subtree, so you create a new node and add 39 into it. Then come to 65, okay? So 65 is greater than 55, so it should go to its right. Right is empty, so you create a new node with 65. Then 57, okay? 57 is greater than 58, so it should go to right. So now you compare 57 with 65. It's less than, so it's supposed to go to its left. So 57. And then 80, okay? So 80 is greater than 50, so go to its right, okay? Then 80 is greater than 50, oh, then 80 greater than 65, so should go to its right, okay? So it's empty, so we add a new one. And then 59, okay? So 59 is greater than 55, so go to right. And then compare with 65, so it's less than 6, so it should go to left. And then compare it with 57, it's greater, so it should go to its right. And there is no branches, so you create a new node for right node for the 57 node. So now we get 59 inserted. Okay, so that's how we build a binary search tree. Okay, so we strictly follow the rule that the left must be less than, the right must be greater than. Okay, the left must be less than, and the right must be greater than. It's always following this rule. Okay. Okay, so here in this example, we discussed how do we build a tree, okay, conceptually. Okay, and then for the binary search tree, is it? So the basic structure that, so the UML diagram for binary search tree class. So it's defined here. So over here, we define the generic one. Okay. But because the binary search tree needed to have that special ordering rule. And when you implement that ordering rule, you need to compare. Okay, with generic comparison, then you must either use a comparable interface or comparator interface, is it? So here we want the generic, any of the generic class, the class for the binary search tree, it must implement a comparable interface, okay? So for a binary search tree, basically, it's kind of like a linked list. We have only one uh, instance variable. Okay, so the root node, the type is a bin node. Okay, and then we have constructor, and we also want to check if the tree is empty. We want to look for some item to search, insert, delete. So those are common operations. Okay, for data structure, and this about traversing. Okay, we will discuss that. Okay, how do we do the traversing? So this is a general definition for a binary search tree. Okay, and before we move to the next section, uh, we can do a quick quiz. Okay, so you can think about after this lecture. So it's a true false quiz. Okay, if it is false, can you explain why? Okay, so the first is in the binary tree structure, there may be more than one path from one node to the other. So it's true or false. Okay, and second is regarding binary search tree, all items are unique. So true or false. Okay, so this will be your own exercise. Okay, um, so that's the information for this lecture. Okay.